Welcome, everybody. Pretty excited today to have you all here. My name is Caleb Lenhoff. I'm the Engineer Channel Manager at Airflow. Today, we're going to be talking about Antec Controls. What you can see in front of me, perhaps, is a venturi valve. We'll get into that a little bit later. Our presenter today is Rachel Peters from Antec. She was kind enough to fly down here from Winnipeg. She's a born and raised Winnipegger. She went to college in Winnipeg, grew up in Winnipeg, and now works in Winnipeg at Antec, which is a subsidiary of Price Industries, which I'm sure you've all heard of. Maybe you haven't heard of Antec, but you probably have heard of Price. Again, really excited to go through this stuff today. Some of it might be review, but I'm actually more excited to talk about stuff like venturi valves and other offerings that Antec has. So I've been working with Antec Controls, and before that, when they were Price Critical Controls, for like 11 years, which I think is how old the Critical Controls department is. So I've been doing this for a long time. I've seen a lot of changes in the industry. One thing that I think is really cool about what Antec is doing is they're continually innovating, coming out with new products, and they've actually been growing like crazy. You guys have like doubled or tripled or something in the last,
for sure,
year or two. Like
Yeah.
I know you've had like huge growth in the last couple of years. So, anyways, again, I'll say it one more time. I'm excited to get going. So I'll just let Rachel get right into it. Thank you.
Thanks, Caleb. So as you said, my name is Rachel Peters. I work at Antec Controls. I'm a senior application specialist. Today, we're going to be going over airflow control devices and room pressurization solutions for critical space. So to start, I'll just go over kind of the agenda for this presentation. We're going to start off going over airflow control devices. So we'll go over 3 different categories, which include our VAV boxes, high accuracy terminal units, and our mechanically pressure independent venturi valves, as Caleb mentioned. Quick summary, and then we'll go into a 5-minute break to kind of close off the first part of the presentation. And we'll get into our room pressurization solutions. We'll go over the different control methods that you can use to create room pressurization. And then we'll get into some of the typical critical space applications that we see and the considerations for each of those spaces. As we are going through this presentation, we'll reference a couple standards, including NCZ 9.5, the ASHRAE Laboratory Design Guide, ASHRAE 170, and the ASHRAE Handbook. If any of you online or in person have any questions throughout the presentation, raise your hand. We have someone here for those online participants that can jump in if you have any questions, and we'll go over those as they come up. So to start, we have our 3 different types of airflow control devices. We have our VAV boxes, which is a flow measuring device, and what we call at Antec electronically pressure independent. And then we have our high accuracy terminal units, which are also flow measuring devices, but as the name implies, they will be a higher accuracy device and as well have a higher turn down than your typical VAV boxes. And finally, we'll have our venturi valves, which are our mechanically pressure independent or flow metering devices. These work pretty differently than the other 2, and we'll get more into the details of that further on in the presentation. So the second 2 devices that we talked about here, the high accuracy terminal units and the venturi valves, are what we call precision flow control devices, because at a worst case, we'll be getting plus or minus 5% accuracy using these devices, where with your typical VAV boxes, at best balancing at 1 airflow, you'll probably get about 5% accuracy. So these are the ones that we see most commonly in critical space applications. However, when applied correctly, we can also control your typical VAV boxes as well. So this kind of shows a side view of what these devices look like. As you can see, the VAV boxes are a straight in, straight out style design with an aerodynamic sensor, making them extremely low pressure drop and as well low noise. In comparison, we have our high accuracy terminal unit at Antec. We call it a VFX. This will also be a blade damper style valve. However, it'll have that venturi shape that'll give it a little bit of a higher pressure drop. And this is actually, like in design, it sometimes sounds like a negative, it'll be higher pressure drop, but that higher pressure drop is actually what allows us to have that higher accuracy and higher turn down, because that larger pressure reading that we're able to get from that larger pressure drop gives us that accuracy and turn down. And then we can see on the right, the internals of a venturi valve, and again, look very different from those other two devices. If you're familiar, we have a spring cone assembly that is actually acting independently of any controls, which is why we call them mechanically pressure independent flow metering devices. But again, we'll get into the details of how that actually works to regulate flow later on. So to start, we'll get into even more details about our VAV boxes. So I mentioned electronically pressure independent, but what does that exactly mean? So I feel like most of you are probably familiar with VAV boxes. If I don't have a controller and I don't have a sensor and I don't have an actuator and I have my damper at a fixed position and there's changes in duct static, what happens?
Flow changes.
The flow changes. So that would not be pressure independent. That means when the pressure changes, the flow is changing. So if we put a sensor in there, we put a controller on there, and we put an actuator in there, and we're continuously sampling that sensor to measure the flow, we can use the electronics to modulate the damper to create electronic pressure independence. So that's why we call our VAV box, our blade damper style valves, electronically pressure independent devices. So that's kind of just like a typical control loop that you'd see on your VAV boxes. That's what we mean by electronic pressure independence. So again, we can see the cutout here. We have our cross-flow sensor. Typically in VAV boxes or legacy terminal units, they will be measuring velocity pressure. But we're not actually measuring velocity pressure. On the inlet of that cross-flow sensor, we will be measuring the total pressure. And then on the back side of that sensor, we'll be measuring static pressure. And then the velocity pressure is the total pressure minus the static pressure. Because we're measuring velocity pressure, this means that these devices are sensitive to the installation conditions, the inlet-outlet conditions. According to ASHRAE 130, we typically require about 3 duct diameters up and downstream of these devices in order to ensure that we can get a steady airflow reading because we're measuring velocity pressure. Another thing, since we are measuring on the front side of the inlet of these sensors, is that they're prone to contamination. In the most cases where you would use these, like commercial applications, office buildings, that sort of thing, it doesn't really matter if the sensor becomes clogged and your airflow reading is slightly off, because typically your main concern would be maintaining temperature control in these spaces. But in critical applications, we're often in environments where there could be large amounts of dust and lint, like in a patient room where they're constantly changing the linens as the patients are changed out throughout those rooms multiple times per day. Or in a vivarium application, you have a lot of animal dander and hair that can clog those sensors. That means that over time, the airflow reading is going to become even less accurate than it was when it was initially balanced. To overcome this, we can install access doors for these devices so that we can do routine maintenance and cleaning to ensure that we have accurate measurement over time, but that's not something that we can do in like a laboratory application where it's corrosive and like you don't want to be sticking your hand in there to clean out lint in a situation where you're putting corrosive materials through those ducts. So this is just kind of a summary showing the airflow ranges and operating pressures that you would typically see in a legacy terminal unit. As you can see, the turn down is typically around 6:1, and your pressure drop and your minimum operating pressure at max flow is very, very low, 0.01 inches water column. The minimum operating pressure, that wouldn't be what you would see all the time. That would just be if your blade damper is fully open. That's what minimum operating pressure means. That's the pressure that you would need in order to get that flow when the blade damper is fully open. So typically you'll see operating a little bit higher than that because you'll want some play to be able to make adjustments. But this is a very low pressure drop and by way of that low noise device. So next, we'll get into talking about our high accuracy terminal units. So these are also doing direct flow measuring and have a blade damper style. However, the type of flow, the way that we measure flow will be different than in a typical VAV box. Across different manufacturers, there's different ways that people do it. Some still use velocity pressure, some use vortex shedding for thermal dispersion. At Antec Controls, our high accuracy terminal unit uses differential static pressure. What this means is that we're only actually measuring on the back of the ports. You can see here a more zoomed in version of the ports. So the flow is going around the ports and the sensors that are actually measuring it are on the back. So that means that we aren't prone to contamination, and as well, you can see that the one of the ports is in that throat, the most condensed part of the valve shape, and that's actually amplifying the pressure signal that we're getting, allowing us to get higher turn down ratios and higher accuracy. In comparison to VAV boxes, the speed of response of these devices is typically faster. And because of the static pressure measurement and not velocity pressure, you're also insensitive to inlet and outlet conditions. So you don't actually need any straight duct in or out of these devices to be able to maintain the integrity of that airflow measurement. So here's a summary table that kind of shows the same thing that we saw for the VAV boxes, but for high accuracy terminal units. As you can see, we can get up to 11-to-1 turn down ratios, but pretty much across the board, we get 10-to-1. This will be something that's needed, especially in spaces like laboratories. You need that higher turn down to be able to account for when you're opening and closing those fume hoods. And as well in places where you want to be able to adjust for temperature control in your high air change environments. One thing to note here is our minimum operating pressure for maximum flow will be much higher. It'll be around 0.3, but that's kind of the cost of having that higher accuracy and the higher turn down. And it will scale between your min and max flow. So we don't usually operate at the max flow of these valves. We typically operate in the middle of their airflow range. So if you're operating lower, it will be lower than 0.3. Finally, let's get into the thing that Caleb is most excited to talk about. We will talk about our mechanically pressure independent venturi valves. So I have a cool GIF here that kind of shows what happens when we talked about electronic pressure independence. We talked about how when there were changes in duct static pressure, that the controller and the actuator needed to move in order to account for changes in duct static. Here, the actuator and the controller doesn't have to move at all to account for changes in duct static. This cone that you can see moving here is actually what's going to be doing all the work when you were at a single airflow set point. This cone is using a real-time force balance equation that it's just doing on its own to be able to adjust. So here we can see when there's an increase in duct static pressure. So the static pressure increases, the cone moves further into the throat, and we can see that the area that the airflow can move gets smaller. So we increase the pressure. If the cone just stayed where it was, the airflow would increase, but the cone moves into the throat to constrict that open area, and then we are actually modulating the flow there to maintain the same flow through the valve. When we have a decrease in system static pressure, the cone will move outwards and will increase the amount of open area that the air has to go through, so that we're still maintaining that same flow set point without the actuator or the controls doing anything. So one thing to note here is because the cone needs to compress and decompress to be able to do this, we actually have a operating range that you need to stay within to be able to maintain the pressure independence. So we have two ranges of valves, either low pressure, that'll be a minimum of 0.3 inches water column, and our medium pressure, which will be a minimum of 0.6 inches water column, and both valves operate up to 3 inches. So as long as you're within that operating range and you want to stay at a single airflow set point, Your cone is doing all the work and the controls don't have to do anything. So one thing that's interesting about that is that in a CV application, if you're retrofitting a CV solution, you don't actually have to put any controls onto these valves in order to maintain a constant volume. You can just mechanically set the center shaft at that position and it'll maintain the same flow without any issues over time.
Is there any future calibration required?
So you can rebalance it, but no, there shouldn't be as long as there's as long as you balance it up front and then it should be good indefinitely. The lifetimes of the springs are extremely long. And a fun fact that we found out earlier is that the springs are actually manufactured in Wisconsin.
Grafton, yeah. A company called Exacto.
Yeah. So this is kind of talking about the other part. If we have a VAV application, then the actuator, I'm just gonna go back and come back to this slide so that we can see the animation again. That's the center shaft movement, and that's what will actually happen to create changes in flow set point. So we talked about when you're at a constant flow, the cone is moving. When you want to change flow, the center shaft is moving. And each position that the center shaft is at corresponds to a unique flow. All of we have positional feedback through a potentiometer, and all of the positions of the potentiometer are characterized in our factory before they ship. And so the controllers actually know at any given position what airflow the device is at.
What does that mean exactly, characterized at the factory?
Okay, so we have 3 different airflow rigs that can operate up to 5,000 CFM each, and we actually run a test on each of these valves, every single one that ships from the factory on these rigs. The rigs have 3 different pressure transducers on them, so they can measure flow accurately with a maximum error of 2% across the full range between our minimum on our 8-inch valve, which is 35, all the way up to 5,000 CFM. And so we actually run, the tests each take about 10 minutes for each valve. We run it at 8 different airflow set points. And then for each of those 8 different airflow set points, we do a measurement at 8 different pressure set points. And through that, we characterize given, because the pressure independent, what it looks like is vertical lines across the pressure for the flow. But we'll be characterizing the position of the potentiometer to the flow that's being measured through these rigs. And that'll actually allow us, because we're not physically measuring flow, it allows us to have a much higher turndown ratio on these devices because the accuracy of the potentiometer and the rigs that we have allows us to measure down a lot lower than you would be able to with the transducer. Because the transducers at those low flows, you can't get the same accuracy. But when we characterize them in the factory, we have an extremely high accuracy transducer that can characterize down to that flow.
Great, so there's, I think what's important here is there's no actual flow reading in a valve like this. The flow that you would read if you have controls on it, and you have to have controls on it to read a flow, I guess you would with a ventur or a VAV as well, but the potentiometer is the position of that center arm, as Rachel said. That's your flow.
And I think there's here, I'll go into this next slide because it calls out where that potentiometer is located. And we can go back and see that when we move that, you can see that potentiometer, which is located right there, is moving. And we're measuring the voltage across there to be able to correlate that to airflow. So yeah, we're using positional airflow measurement based on a potentiometer reading, extremely high accuracy potentiometer. Some of the things that we see here is again, we can get up to a 20-to-1 turndown ratio on these devices because of how low we can go using positional measurement instead of direct measurement with a transducer. Again, these are, because we're not actually directly measuring anything, these are extremely resistant to contamination. There's no ports to be clogged. We're just measuring with that potentiometer and the center shaft. We get that at worst case, plus or minus 5% accuracy. And again, these are completely insensitive to installation. We don't need any straight duct up or downstream of these devices. These, again, as discussed, have a pressure range. So they have, out of all the three, will have the highest pressure drop, but because the cone is actually responding instantaneously to changes in duct static pressure, there's no controller to read and adjust. This will be the fastest response time of all of these solutions. This is kind of a summary again of what you'll see across the different types of venturi valves. As discussed, we have our low and medium pressure valves. The main difference here will be the top end flow. So we'll still have the same minimum flow across these two devices, but for the low pressure valves, you will be losing a bit at the top end and have that a bit of a lower turn down ratio than our medium pressure venturi valves. And here's a quick summary to go over the three technologies that we talked about. As discussed, the terminal units and the high accuracy terminal units are electronically pressure independent, so they require a controller in order to maintain that pressure independence, versus our venturi valve is mechanically pressure independent with that spring and cone assembly. The terminal unit is measuring velocity pressure, where the high accuracy terminal units are measuring differential static, and the venturi valve is actually measuring position. The airflow feedback for our terminal unit and high accuracy terminal unit is measured, whereas our airflow feedback for the venturi valve is electronic. Our terminal units will not be contamination resistant, where our precision airflow devices will be resistant to that contamination in the airstream. The turn down ratio for our terminal units will be around 6:1, high accuracy 11:1, and venturi valves up to 20:1, depending on the pressure range. And then again, the pressure drop will increase as you increase in turn down. And then the typical VAV boxes, they'll have a 3 duct diameter requirement upstream, downstream approximately, where the high accuracy terminal units and venturi valves will have no straight duct requirements in order to maintain their airflow readings. And then for the construction, our terminal units will be galvanized steel. Our high accuracy terminal units will be aluminum, and the venturi valve will also be aluminum. For coatings, we can see this venturi valve here has coating on it. It doesn't look aluminum. This is our phenolic class 1 coating, which is available on our venturi valves as well as on high accuracy terminals. This would be what you would see in most teaching laboratories. It creates corrosion resistance. On our venturi valves, we do also offer phenolic class 2 and Kynar, which will be resistant to the more corrosive chemicals that you might see in research type laboratories. Now we'll take a 5-minute break. If anyone has any questions, or if you want to come up and see this venturi valve, feel free to do so.
The controls and jobs were special ordered removable flow sensors.
Mhm.
Is that ever going to become a standard option versus this special flow type situation?
Sorry, for the terminal unit, you want removable sensors?
Well,
It is a standard known one.
it is a standard.
Yeah, you can get removable flow sensors on terminal units. So you're saying you could put an access door in there.
Yeah.
Another option is you actually have a removable sensor that you can pull out and clean if you need to,
Or just replace them in some cases.
or replace them.
Yeah.
But yeah, it is a standard now in all-in-one. Select that option.
Yeah, so our terminal units, so Antec doesn't manufacture the terminal units, they're actually manufactured by Price.
Correct.
But we can put our controls on them to use in critical space applications, more typically on the supply side, because that's where like contamination resistance won't be as much of an issue. But yeah, anything that's available through Price, we can do whatever they do, so. And we do have the option to either have the controls be mounted in the field, or we can factory mount them, but then they'll just have to be, it's a little bit of an added cost, because they'll be shipped up to Winnipeg and then shipped back to wherever they need to go.
So I believe this is the simplest answer, but the difference between a low pressure and a medium pressure is purely the spring, correct? Or is there something else in there?
So, fun, There's actually no difference between the low and medium pressure construction. It's the way that we characterize and test them.
Okay.
And the main thing is that if you only have 0.3 inches of pressure, when that cone is fully extended, you physically do not have enough pressure to get those maximum flows, is the main thing. So it's characterized differently, so like the curve that we characterize it with will be different. And then also, it's mainly that we can't get to those maximum flows, so it's factory characterization is different, physical construction is identical, so you can't just swap from the field because the characterization will be different. But yeah, it's mainly a difference in the way that we test them.
Good question.
Back, just before we get on to the next thing. Any questions on venturi valves? There was a question during the break about the characterization. Again, it's tested at the factory throughout the pressure range. And the difference between the two pressure ranges, so low pressure and high pressure, or medium pressure, is actually the same spring, but at the lower pressures, you can't measure higher flows. Correct?
We can't achieve the higher flow.
Can't achieve the higher.
It's just not enough pressure to be able to actually,
That spring bottomed out, right?
yeah.
Okay. Anyways, so that's interesting. Just a teaser, we are going to be doing a Winnipeg trip later this year. We don't have the dates yet or the details worked out on that. But we would do a tour of those test rigs, and they're pretty impressive. And like Rachel said, every valve is tested at the factory throughout its entire pressure range, and it comes off of that rig at or better than the plus or minus 5% of the flow. There was also a question in the chat from Anonymous about controls, and if you need to purchase a software package for the Antec Controls. We will get into more of the controls theory. The short answer is no, there is no software necessary to use the Antec Controls. The caveat on that, in other words, we have a controls option that can be sort of controls by others in the BAS that works well with controls by others. There also is a full controls package, but again, we'll get into that in a little bit more detail. So without further ado, take it away again.
Oh, there you go. Okay. So now I wanted to get into talking about room pressurization. We talked about valves and the airflow control devices and the fact that we want precision airflow control devices, but why do we want precision airflow control devices? It's because in critical spaces, these rooms need to be pressurized. Pressurization is important in these spaces because it creates directional airflow. And we, in critical spaces, say we want the air to always be flowing from clean to less clean spaces. So in our negatively pressurized spaces, those are spaces where those are the less clean spaces, maybe a laboratory or a sick patient. We want to make sure that the air is always flowing inwards to those spaces. And that's why we want that pressurization. Versus in positively pressurized spaces, that might be a clean room or an operating room. We want to make sure that the air is always flowing outwards of those spaces to keep the patients or the things that we're manufacturing clean. Pressurization is created when there is a difference between supply and exhaust flow in and out of a space, or differential airflow. So in a positive space, we will have more supply and less exhaust. In a negative space, we will have less supply and more exhaust. The magnitude of this pressurization will depend on the magnitude of that differential airflow or the flow offset. It will also depend on the room leakage. Here we can see kind of a graph that shows how room leakage and what that differential airflow needs to be in order to achieve the pressurization set point in these spaces. So this can also, the amount of leakage will be affected by local construction practices, ceiling types, and door selection, as well as we've seen some spaces, especially in pharmacies, where they put sealant around every single hole, those will be very tight, low leakage spaces. Thing about low leakage spaces is that a small change in airflow or in your differential airflow or your offset will create large changes in room pressurization. So this is just an excerpt from ANSI Z 9.5, which is our laboratory standard. Space pressurization or directional airflow between spaces is one of the many tools available to limit exposure to laboratory hazards. Effectively applied, it opposes migration of air contaminants, but it does not eliminate it. Air moves between spaces in response to many phenomena, including thermal effects, movement of people, and direct drafts from the ventilation system. Effective pressurization overcomes many of those drivers most of the time. In a laboratory with ordinary construction and a properly functioning ventilation system, air can move briefly the wrong direction. So this image that I have here is just showing that this would be where your leakage is coming in, and negative pressurization means that anywhere where leakage could occur, it's always moving into the space if it's negative. Versus if it's positive, anywhere where leakage could occur, it's always moving out of the space. Now, there's two main methods of creating this room pressurization. The first is known as direct pressure control or active pressure control. And this is where we have to directly measure the pressure in the space. And then we will be making adjustments to the flows in the space in order to maintain that pressurization. So typically this would be done through some type of PID loop, which means that over time, like it will be measuring over time and making adjustments. However, it also means that if you have your door open, if there's nothing to tell the PID loop that your door is open, that it will continue to try and make those adjustments. And it's not reasonable to try and maintain pressure when your door is open. So in a negatively pressurized space, it might be continuing to try and open that general exhaust valve, and it will be fully open. And then when you close that door, your room will be extremely overpressurized. So because of that, we highly recommend that when you are using direct pressure control, that you include door contact switches so that it can detect when that door is open, and then while the door is open, it will pause, you have to control the pressure in that space. And then you will, when the door closes, it'll resume from where it was, which is likely pretty close to where it needs to be. And you won't have that wind up in your control sequencing.
Question from Jason in the chat, are the leakage curves CFM per SF?
Yeah, so this will be, the different lines will be your square feet, and then the bottom will be your differential. So like the
Just pick a point, for example, so the square, so each line is the square feet of leakage in an area, right? So at 0.6 square feet, you'd need 200 CFM to get a 0.014 or so. Ish differential pressure.
And this will all be theoretical when you're putting together your designs. And so one of the things about this is it'll always be balanced on site, because you can make these assumptions of what leakage will be, but again, if the site itself is putting caulking around every single hole in the space and that wasn't something that you would accounted for, this is something that can be balanced on site if the leakage in the space doesn't end up being exactly what you theorized that it would be in the design phase. Does that answer, hopefully that answers the question? Okay, so back into direct pressure control. Because we are continuously measuring and adjusting for that room pressure, one of the advantages of direct pressure control is that we can account for changes in room leakage over time, because we will be continuously making changes to adjust for the measured pressure reading in the space. Again, because it is kind of a PID approach, typically the direct pressure control is best applied in environments where you're not having large changes of airflow and there's lower traffic. Because if there is a lot of doors being opened and closed, again, it can create instability in your control, as well as if you have large changes in airflow, whether that be for temperature control or for like, for example, an opening fume hood, it'll be more difficult to tune your PID loop to be able to smoothly and stably control the pressure in those spaces. And again, because we are doing a PID type approach, it'll typically be a slower speed of response than our second method, which is volumetric offset control. This is the approach that we see the most common in critical space applications because a lot of them do have higher traffic and larger changes in airflow. This sometimes is also known as flow offset control. This is where we are controlling to a difference in supply and exhaust. So in pressure control, direct pressure control, where we just talked about, we are controlling to a pressure, and while controlling to a pressure, we will essentially be creating an offset between your supply and exhaust by way of controlling to the pressure. This is kind of the opposite of that, where we are controlling to an offset in the space. And by way of having that offset, we are creating a pressurization in the space. This is again one where we will need to balance the exact offset that's required in order to get that pressure reading on site. But as long as there's not large changes in room leakage, if you're not punching holes in the wall, like once you balance it, that offset should maintain that pressurization over time. So because we are controlling to an offset, this will be a lot more stable because we are just controlling to the difference between the total supply and total exhaust in the space, as well as it'll be a faster speed of response, especially when there's large changes in airflow in the space. For this, we don't require a pressure reading, but we can have pressure measurement and door contact switches just for monitoring purposes, especially in your applications where pressure monitoring is required. We will still see flow offset control used, and then also have pressure monitoring for alarming purposes. So this is just an example of kind of how flow offset would work. This is a lab where you have a supply and a general exhaust and 3 fume hoods targeting an offset of -200 CFM. And negative meaning that there's more exhaust in the space than supply. So if we open one of our fume hoods, typically the speed of response of a fume hood is around 1 to 3 seconds. So we open one of the fume hoods and it'll go up to 600 CFM. So within 1 to 3 seconds, we are going from 70 to 600 CFM on our fume hood. And then as you can see in our general exhaust, we're actually going down from 790 to 260 CFM in that same period of time. And because we know and have balanced the room to know that the offset just needs to be -200, instead of us needing to continuously measure and adjust, we know exactly the set points that these valves need to go to in order to maintain that pressurization in the space. So that's kind of where the speed of response of, like the faster speed of response with offset control comes in, as well as stability. If you're continuously opening and closing fume hoods, especially in something like a teaching lab, this will be a lot more stable than direct pressure control. So now we'll just go over some different standards and what they say about room pressurization. So to start in ANSI Z 9.5, they say it is impractical to maintain a differential pressure across an open door. That's kind of what we talked about with direct pressure control, and hence why we highly recommend the door contact switches, because you can't, when the door is fully open, there's no way to maintain pressurization in that space. ASHRAE 170 says that short-term excursions from required pressure relationships shall be allowed while doors are moving or temporarily open. And if pressure monitoring devices are installed, allowance shall be made to prevent nuisance alarming. And now the way that we typically prevent nuisance alarming is through the use of door contact switches so that we can turn off alarms while those doors are open, because we know that the pressure is not being maintained. The ASHRAE handbook says that direct pressure control sequences function best in the presence of slow disturbances only, whereas fast disturbances such as VAV fume hoods are explicitly listed as a factor that favors the flow offset control solution. Our ASHRAE lab design guide says the HVAC system for a laboratory is often subjected to rapid disturbances or changes, such as those caused by opening doors, opening sashes on numerous fume hoods at once, or turning on large pieces of heat generating equipment. question.
From Jason, what is industry standard for time delay of active pressure control and doors being open?
I'm gonna make an assumption of what that means is that when the door is open, like how long?
Is the question, how long is a door allowed to be open? Or state the question again.
What is industry standard for time delay of active pressure control and doors being open?
So pretty much while the door is open, there will be no controls, because regardless of how long it's open, you're never going to be able to maintain pressure across an open door. However, in spaces where maintaining that pressure relationship is critical, we'll often have a time delayed alarms, maybe like 60 seconds. And say, while the door is open, don't alarm, but after 60 seconds, if the door is still open, then we should alarm and say either your door is open or your room is in low pressure.
Said, how do you prove 60 seconds maintains containment?
So you won't be able to maintain containment while the door is open. It'll go neutral during that period of time. But it is an allowance that's made by the standards and by the industry. You have to be able to enter and leave those spaces. But, and that's something where as well, you can evaluate the criticalness of the space you're in, like in a high school laboratory. That won't be a space that's as critical as something like an operating room. So the alarm delays that you'll have in those different places will be different depending on the application. So it's something that's their like industry standard might be something like 15 seconds in one application, 60 seconds in another. It really, it comes to evaluating the risk for each application that you're working in.
In some highly critical spaces, they would have a vestibule probably.
Correct. If it's something where it's like an absolute safety requirement that you can never lose any containment or pressurization, you would have an ante-room. So you would have a room between the two rooms so that pressurization would never be lost. We see that often in clean room applications where the cleanliness of the air in those clean rooms for like microelectronic fabrication is really, really critical. Otherwise the manufacturing process won't work. You will have those vestibules or ante-rooms to prevent pressurization from going. But in your less critical applications, then it is acceptable to have those periods of time where you don't have containment to allow people to enter and exit those spaces.
Regional Jason added, pharma applications get audited and FDA/EU don't allow time out proof.
Yeah, so are you specifically talking about clean room applications or compounding pharmacies? We have clean rooms, yeah, so in clean room applications, we would typically see a vestibule or an ante-room. And we would have pressure monitors at those spaces that would be tied back to a BMS to be able to trend that pressure at all times to make sure that pressurization is always maintained. Yeah. Good. Okay. Getting to the next one here. Such factors lead to flow offset control as being the most commonly applied approach to room pressurization in laboratories. That's tying back to the large changes in airflow from opening doors or opening fume hoods or large heat producing equipment. And then NCZ 9.5 also says 10 seconds will be an acceptable time to achieve the desired area pressurization subject to any hazard evaluation. So that kind of gets back into what we were talking about with Jason's question there is 10 seconds will be an acceptable time to achieve the desired area pressurization subject to any hazard evaluation. So if you do a hazard evaluation and evaluate that it is something that's going to be hazardous to take longer than or less, 10 seconds won't be enough, then there can be other changes made to the system, whether that be ante-rooms or other things like that to be able to account for increased hazards. So now we'll get into some of the typical applications that we see at Antec Controls in critical spaces. The first is compounding pharmacies. So some Some considerations for these spaces. As you can see, we have a render kind of a layout of a compounding pharmacy here. And one of the things that affects compounding pharmacies is pressure cascades. So that's where like the pressure in one space will pressurize the other space, but in cascade. Here we have 3 rooms in a pressure cascade, but some compounding pharmacies can have up to 7 pressure cascades. And when you're doing that, if you're using direct pressure control, that's something where you have to be very careful about tuning in stability, because if pressure in one space changes, it cascades and it'll affect all the other spaces, and they will have to modulate and adjust for that. So in these types of spaces, we do typically see flow offset control, but direct pressure control can also be used as long as it's tuned properly. Another thing in these spaces is that they have extremely high air change rates and tight construction. So when we're talking about pressurization and leakage, we're saying if you have like low leakage and you have these high airflows, small changes in airflow can create large changes in pressure. So for example, in these types of spaces that are also very small in terms of room volume, we might need 1,000 CFM to maintain the ACH required in these spaces, which is about 30 in your sterile compounding. If our worst case error is plus or minus 5%, that's 50 CFM. In these small, tightly sealed spaces, you might only need 20 CFM to actually maintain the pressure set point in these spaces, which is within that range of error. So sometimes in these spaces, if they're over sealed, it can be very difficult to balance these rooms. So sometimes they actually have to add transfer air through these spaces to increase the leakage, because otherwise it's just impractical to maintain pressurization in these spaces without there being volatility. Another thing in these spaces is we don't usually see fume hoods, but we do see biosafety cabinets. They are typically either constant volume or 2 position. If they are constant volume, then typically the whole space will just be standard speed actuation, which will be the 95-second full stroke actuation. If they are 2 position and they have high speed actuators on biosafety cabinets, then you would also want your supply and general exhausts to have high speed actuation, so the whole room can have the same speed of response. So they'll just kind of get into what the standards say about compounding pharmacies a little bit. This will give a little bit more context to why we have those 3 rooms. Our hazardous drug rooms will need, even if they're non-sterile. So sterile compounding is where you want the room to be free of contaminants and microorganisms. So that's why so if it was non-hazardous, then it would be positive, because typically you're trying to keep it safe, so you need a positive. But then if it's hazardous, you want to keep the hazards in the room, so then it'll be negative. So if you're doing hazardous and sterile compounding, that's when you need that anti-room. So complicated. And again, in the sterile compounding across the board, we have that 30 air change rate requirement, very high for these small spaces. Non-sterile, we have 12 ACH for the hazardous and 4 for the non-hazardous. This will kind of get into that first render that we showed. This is kind of what those pressure relationships would look like. So the anti-room would be positive, and then on the right side we have positive. So this would be your non-hazardous sterile on the right side, and then it would be your hazardous sterile on the left side. So as you can see, we want the air going from clean to less clean, so we're keeping the hazards negative to the anti-room. But the anti-room is also positive to the corridor because this is sterile compounding. So we need the positive pressurization to make sure that the hazardous room is still maintained as sterile. And again, another thing to note here is you can see that there's room pressure monitors outside of each door. This is required by the standards and can be, if it's native BACnet, tied back to a VMS for constant monitoring. Yeah, you'll see it outside of each room as well. So if we go back, we can see if we have the non-hazardous drug room for sterile, that would be our right room. So that one will be a range of 0.02 to 0.05. And our hazardous drug room will be 0.01 to 0.03. And then our anti-room will be a positive 0.02. So another thing that I noted there was a range. So typically in our healthcare applications, we have a minimum pressure requirement. In compounding pharmacies, we have a pressurization range, which makes it even more difficult to balance, because if it goes above the pressurization, it's still unacceptable. Versus in most applications, as long as you meet that minimum pressurization requirement, you're good to go. So it's just another layer of complexity to these very small, tightly sealed, high air change rate spaces. Any questions about compounding pharmacies before I move on? Okay, so the next application that I'll get into is isolation rooms. So this would be your most typical healthcare application. One of the main considerations here is the isolation room type. I'll get into more of the different types in a couple slides later. And the type of isolation room that you have will also affect whether or not you need an anteroom. One of the things to note is that according to ASHRAE 170, pressure monitoring is required for all isolation rooms. And then another consideration of these spaces is because the patients are essentially living there, a lot of isolation rooms will have ensuite bathrooms. So we do also want to be cognizant of the bathroom odors as well. Here shows like a kind of a pressurization diagram of two of the different types of isolation rooms. As we can see, we talked about airflow going from clean to less clean. So if we have a patient that has an infectious disease, they are the less clean. So we want a negative pressurization relative to the corridor. So you want airflow flowing inwards because the patient that's in this room has an infectious disease. We want to protect people that are outside of the room from that disease. And then again, we want the airflow to flow from that room into the bathroom so that the patient is not disturbed by the bathroom odors. So that's our airborne infection isolation. The second kind is protective environment isolation. So this would be when you have a patient that is immunocompromised. You want to make sure that they are kept safe from the other diseases or contaminants that could be out in a hospital. So we want that positive pressurization. So we want the room itself to be as clean as possible. So we're flowing from here outwards. And then again, we want the flow to go from the room into the bathroom to protect that patient from those odors. So what happens when you have a patient that has an infectious disease who is also immunocompromised? Anteroom. So we have the anteroom that will make it so that it's positive relative to the corridor. So we are keeping that patient safe from the contaminants that are out there in the hospital. But we also will be negative, the room itself will be negative relative to that anteroom in order to keep people in the hospital safe from the infectious disease that that patient has. So you're double safe. The patient is safe, the hospital is safe, the anteroom is positive. And then again, the bathroom, you'll have that negative to the space to so that the patient can have a pleasant experience. And again, I'll go back to the pressure monitoring. When we do have that anteroom, we actually need 2 pressure monitors in there as well, according to the standards, so that we can make sure that the pressurization is maintained at all times. Oh, I should have asked any questions about isolation rooms? Nope. Okay.
You did such a great job. There's just no
No
questions.
questions. Next is another healthcare application. This would be our operating rooms. Operating rooms are a little bit different because there's slightly different considerations than a patient room because the people aren't living in here. There's actually like pretty high traffic in these spaces because you could have like multiple surgeries per day in the same room. And it might actually be a different team of surgeons doing each of those surgeries. And each of those surgeons might have specific temperature and humidity requirements that they need. And so we need to be able to quickly adjust the temperature and humidity in these spaces between surgeries. Unlike isolation rooms, pressure monitoring isn't actually a requirement. However, for the most part, we do still see pressure monitoring in operating rooms, as well as we often see a larger monitor on the wall At Antec, we offer the MVM, which is a larger monitor to display the temperature and humidity in the space so that the surgical team can like quickly do a glance at the monitor on the wall and know that everything is good for them to keep going and feel confident in doing their surgeries. Another thing I want to talk about here is the diffuser and grill placement. So in operating rooms, it's required that 70% of the area on top of the patient table, the operating table, is diffusers. And that creates that laminar flow downwards onto the patient. And then we'll have grills at the bottom of the room to create that, so the curtain comes down and then the flow goes outwards like this, so that we're always putting clean air over that operating table and then it's leaving the space. Because of that, sometimes lighting can be an issue. We do at Price, our sister group, Critical Environments, they offer something called Ultra Suite, which is they have the diffusers that actually have HEPAs and lights all integrated into one system. So that can actually help, because otherwise if you have the whole grid of diffusers above the patient, the only lights you have are pretty far away from the operating table. So that can also be a concern when you're working in operating rooms. And again, because all of the airflow in the space is coming down above that patient table, your operating staff is standing right underneath it. So that's why temperature control is much more of a concern in operating rooms versus in other critical applications. Because we have the air, all of the airflow in the room is essentially coming in on top of the patient and the team itself. It'll typically also be a colder temperature set point, yeah.
Heidi had asked, how long post-operation do you need to maintain laminar flow before setback to unoccupied?
I would actually need to look into that. I'm not sure how long that is. We do, I can look into that for Heidi and get back to you guys. But we do offer, yeah, a setback. That's another consideration for these spaces, because operating rooms, when they're running, require 20 air changes. And because of all the large equipment in these spaces, these are actually high volume rooms. These are large rooms. And so maintaining 20 air changes in these large spaces is like a large drain on the energy. So they're typically, if they're not rooms that are being used 24/7 for operations, they will have a setback, like Heidi mentioned. I'm not sure what the timing between being able to go from occupied to setback is, but I'll look into that and I'll let Caleb know and he can communicate that outwards. Yeah, so again, high traffic, high flows. Typically we see offset control in these spaces because people are going in and out of the room as the surgery is progressing. There will be different types of people that need to join the surgery at different points. And so those doors will be opening and closing, and we would most typically see offset control. But again, if it's tuned properly, direct pressure control is also an option in these spaces. Any other questions about operating rooms? All right. Next, we'll talk about laboratories. So we did a little bit of an example with laboratories and offset control earlier, but I would say one of the main considerations of laboratories is your fume hoods. So your fume hoods will have pretty large airflow ranges. On a typical 4-foot hood, you will probably be operating between, at your fully closed, around 150 CFM and your working height around 600 CFM. And so if you are opening that, and it'll, as NCZ 9.5 says, you should open at 1.5 feet per second. So it'll be a couple seconds, you'll be opening that, going all the way from 150 to 600. You want to be able to control that within, according to the standards, 5 seconds, but industry, I would say, expects it to be controlled within about 1 to 3 seconds. So these will be high-speed applications. If there are fume hoods in your laboratory, the fume hoods will always have high-speed actuators on them. And because of that, your supply and your general exhaust will also need to have high-speed actuators to make sure that the room containment can be maintained. Fume hoods are what we call the primary containment, because that's where you're doing those experiments. But your room pressurization is your secondary containment, so it still needs to have that same speed of response. Because if you spill something in your laboratory, you want your room to be able to contain that and keep the rest of the building safe from those chemical spills. Yes?
So everything we've kind of been talking about with laboratories is assumed a constant volume. For the most part, right? Like when you're talking about offset and everything like that, when we get into a setback application where we'll have a laboratory exhaust fan. A lot of times we're going into bypass mode where we're maintaining the same.
Are you talking
Just-
about the fume hood specifically?
I'm talking about the lab in general.
Oh, yeah, so, well, there's multiple options. There's some laboratories that, to your point, will, like the fan itself will be a constant volume application, but there are also fans that you can get where it kind of like pulls in,
We entrain air and
Yeah.
bypass air to
to be
maintain.
able to maintain that plume height. So it
Yes.
does allow you to turn that fan down and still maintain the plume height, when you are in setback.
Yes, so in an instance where there is setback, here, I'm assuming that's when we get feedback to the potentiometer. The potentiometer then moves the valve to set a different set point, correct? I just wanted to be clear, that's how we're achieving that with the valves.
Yeah, so anytime that there's a change in airflow set point, our potentiometer will be reading that and we'll be making adjustments. So setback, like in terms of the exact numbers, I would say typically when you are operating using a fume hood, you need about 100 feet per minute through that open area. And that's when someone's actively using it. In laboratories, like at a university, teaching labs, there might be fume hoods that are unoccupied. Then we can have an occupancy sensor to sense when someone is there. And then when they're not, we can set back to a lower feet per minute set point. Typically, I would say somewhere between 60 and 80. It depends on the hood type though. I believe the requirement is somewhere around, it's like 175 to 350 hood air changes per hour. So as long as you're still getting that low end of the hood air changes at that lower base velocity set point, you can set back to that low. And then yes, typical occupancy, there's multiple different types of labs. So in your teaching labs, you might have people in there only once a day for a few hours. And in that time, you'll have like 20 or 30 students. That is a large change in thermal load. So you have to be able to account for when there's large thermal load, but also when there's not. So you need to have a little bit more flexibility in those types of spaces versus in a research lab, you might have between 5 people, like around 5 people in there throughout the day. So it's a bit more of a consistent temperature load in those spaces.
Before you move on, so I teased a little bit before this section, the different types of controls that we offer. So these are the application overviews,
Yeah,
right? Can you talk a little bit about each of the control options that we would have? And let's use this lab with the fume hoods as an example.
so for your supply and general exhaust valves, well, in all these cases, the controls that Antec Controls offers are a distributed network that talk to each other over like a high-speed network. So regardless of which controllers you have, they're all talking to each other. On our supply and our general exhaust valves, we would, if we were the ones providing controls, we would offer a pace controller, which is our room controller. And that would control your valve to its set point. It would track your fume hoods as it's doing that. But we also offer, depending on the valve technology that you're using, controls by others solutions. So if you're using a venturi valve, we have what's called the LMX. And that'll, like we talked about the characterization curves, that'll output an analog signal that will take that characterization curve, read that voltage, and then use the curve to output what flow that is. That can then be used by a
Keep going.
BAS to control, or someone else's controller to be able to control that. If we want to say a VFX valve or a high accuracy terminal unit or a terminal unit, that's again flow measuring. So in those situations, we would have the same controller if we were doing controls. But if we wanted to do a controls by others solution for that, we can offer a pressure transducer to be mounted on those valves to provide a pressure reading to the controller that can then use that to control those valves.
So, let's quickly just talk about those for a second. So this is what the pace controller looks like. The pace controller, there is a software commissioning tool, but once it's commissioned, through BACnet, the front end can talk to that, monitor what's going on, and can change some set points, correct?
Yeah,
So you don't need the software necessarily if you want to make some changes to your lab. To commission it, you do need that. We would, be able to provide you with that. Or if I do the startup or something, I could come back if there's any changes, that kind of thing. So that's the pace controller. The LMX, going back to that really quickly, all it does is give you an output signal that's linear to the flow. So you have your 2 volt, which is your minimum flow, to your 10 volt, which is your maximum flow. What you would do to control that is you would actually send a 2 to 10 volt signal to the actuator itself. The actuator would move it. So 2 volts to the actuator may or may not be the minimum flow that's output by the LMX. You can see when you move it to a position, the potentiometer in here reads the position of that arm. So this may be 8 volts. The voltage of the potentiometer goes to the LMX and that outputs a voltage that is going to be your flow. And on here, we don't actually have it, but there's usually a sticker with a graph of the flow. It'll show your input, or well, actually it'll show your actual flow and then the linear flow that the LMX outputs. And then eventually it just operates like any other control device. You give it a signal, it tells you what it's doing. And then you do the rest of the room controls. Now, if we do supply the pace, we would provide all of that room specific control. And then I'll let you keep going with how you were explaining controls. We can talk about the fume hood controllers a little bit as well.
yeah. So just to Caleb's point about BACnet, I know the question earlier asked about how integration with BMS. All of our controllers, as well as all of our pressure monitors, are native BACnet MSTP, so they can be integrated into your BMS. And again, we can provide data for visualization, as well as we can accept overrides for specific set points after the controls have been installed. So that would be your room level control for your supply and general exhaust. For your fume hoods, what we would have is we would have a monitor that's actually mounted onto the fume hood. Our fume hood controller is called Cava. It's a touchscreen fume hood interface because we do want to have the current feet per minute through that fume hood displayed to the user at all times to ensure safety. One thing about fume hoods is there are different types of fume hoods, and I don't have any slides for it here, but there's different sash configurations on fume hoods. The sash is the thing that we're opening and closing to be able to do experiments inside. What we have is we have a vertical sash is the most typical, where it just goes up and down. In that case, we can put a sash position sensor on it, and we can just measure how high the sash is, and we know the width. And if you know the height and the width, you know the open area. And if you know the open area and you know the flow, then you can calculate the feet per minute, and you can modulate that flow to make sure that you maintain that feet per minute set point. If you have a horizontal sash, that would be where they open horizontally. You can't put a sash position sensor on it in the same way. What we do for that is we have a sidewall velocity sensor that's actually measuring the differential pressure between the inside and the outside of the fume hood, which directly correlates to the feet per minute going through that hood. And so that would be more of a PID control approach, where we would be continuously measuring the actual feet per minute through that fume hood and making adjustments to the valve in order to maintain that set point. You can also use sidewall velocity sensing with a vertical hood. It's not limited. And then for a combination type hood, that would be where you can both lift it up as well as there would be panes to move horizontally. Again, there you would always want a sidewall velocity sensor for those horizontal panes, but you could also do a hybrid approach where you combine both the sash sensor and the sidewall velocity sensor to utilize both the quick speed of response from being able to calculate the open area and know the flow, as well as the closed loop of the sidewall velocity sensor to be able to make adjustments in case there's obstruction in front of your fume hood that are affecting the base velocity.
Great.
Good.
Yeah. And then again, like, you already showed the example of this, so either if you're going to control the room offset, we provide the Cava fume hood controllers with the valves. And as the sashes open and close, they go to a position, the VAS would read that. And then same thing with the supply and return, you'd send a signal to your supply to give it a different flow to maintain that offset. So the pace controller does that. It talks to all the other controllers in the room, does it all instantly, but it is available to be done by others if you don't want to use those controls. So just different ways to do it. I think having I've seen a trend where people are going towards wanting to do everything through the BAS, but this is really simple. Lab like this, if the fans are running, the boiler's running, and everything is balanced, we can set up this lab in an hour or two. It's super simple using our controls, so that is an advantage to maybe using controls by Antec for full room control solution. But again, we work well with others, so we're not picky.
Yeah, and to your point, when we are doing the full room controls, we do only require one backnet drop for the whole room to be able to communicate everything because it is a distributed network. We do have all the information about all of the valves in the room from a single connection point, as well as when you're commissioning the room, similarly, there is a single connection point that you need to plug into to be able to set all the settings for all the valves in the whole room. Caleb alluded to our startup software a little bit. It's a software called Antec Toolbox. It is something that we do require training for people to be able to use. However, we do offer facilities and owner training because I know that some facilities do want to have that autonomy over their systems. We can do an abridged version of our training that focuses mainly on the aspects of the tool that the facility would need to use to be able to do maintenance on their own system. And then we will provide software free to anybody who does that abridged or full training, depending on what they're looking to use the software for.
Great.
So to summarize, the second section of the presentation, room pressurization creates safe environments by making air move from clean to less clean spaces. We can create room pressurization through direct pressure control or volumetric offset control. Leakage must always be considered when selecting sequencing to ensure stability. And as we mentioned, in very low leakage spaces, we may need to even add transfer air to allow for stability of control. And each application that we have has unique challenges and requirements, and they can be overcome by selecting the right equipment and control methods. And for those of you that are newer to designing these spaces, if you require any guidance or assistance with that, that's something where you can reach out to Airflow or to us, and we can work together to help you through these more complex critical spaces. Are there any more questions?
In a lab space application, can you describe when you would use a high accuracy terminal versus a venturi? Because I've seen obviously other manufacturers that are specified. I mean, so sometimes we'll see Phoenix, sometimes we'll see AccuTrol.
Yeah.
What are the benefits versus, what are you giving up in using a high accuracy terminal versus a venturi in your lab that you were just showing there?
So for the most part, I would say that it comes down to preference of the facility, of the owner, what they're looking to do. The the thing about the venturi valves that we talked about is it does have that instantaneous speed of response with that cone moving to changes. So when you have multiple fumes on the same manifold, the stability will be higher when you have that venturi valve. But we can achieve highly stable and also fast solutions when you tune your PIDs correctly when using high accuracy terminal units. I would say the main application where we would always see venturi valves would be in the more corrosive applications, because I have to go back to when we talked about the comparison between the three. The VFX, our high accuracy terminal unit, is only offered in our what we call P1 coating, which is we still have stainless steel internals. So when you're working in more corrosive applications, that may not be enough. We can provide compatibility information about all of the different coating options. But our venturi valve, we can do up to a Kynar coating, and it would have fully Teflon internals. So in your more corrosive applications, you would need to move with a venturi valve. But if you're in lower corrosion applications, both technologies will be fast and acceptable.
Are they compatible to work in the same lab, or do you?
So
Would you
we
ever
don't
have-
recommend putting them on the same manifold. They could be in the same lab if they're on different manifolds. But for
So
the
you could use supply side, you could use a VFX, whereas you'd use a Venturi on the exhaust.
correct, we actually do see that quite a bit where we'll have like even a terminal unit on the supply, like a VAV box on the supply, and you'll have your venturis on your fume hood exhausts. You can mix and match, but yeah, you don't want them on the same manifold because it will create instability in your specifically in the depends on the ratio between the two that you have. But if you have a lot of venturi valves on one of the manifolds and then you put a blade damper valve, it will create instability for that blade damper valve.
So for instance, in this application, because your 3 fume hoods are on the same exhaust as the general, you would not be able to mix and match devices there. However, you could have whatever you want on the supply in this application. And generally, something like this, your supply is going to be constant volume or modulate for temperature control. And then the way that the offset is controlled is through the general exhaust. So you don't really need a fast response on your supply side. And as the supply changes, the general exhaust, is obviously going to keep up if you have a slow acting control on the supply. Have you seen labs where they're doing like decoupled cooling and heating? So in other words, like chilled beams in a lab situation. And are our controllers able to work with something like that to control, like say a chilled beam?
Yeah, so now that I feel like right now we're in a period of time where energy efficiency is like really at the forefront of people's minds. So we have started to see more chilled beams in our applications, and we can do that in conjunction with laboratories. We're actually working right now on a big project in Texas at one of their universities, and they have 5 or 7 floors of labs, and they're using chilled beams for controlling all the spaces.
Very cool. We kind of flew through this. Are there any other questions or any other things anybody wants to see?
Just a quick, like if I'm designing this same lab as an example, I just wanna know like all the controllers that, if I'm selecting or something like that. So I just wanna reconfirm, so there is a pace controller that goes with the venturi and Kawa that goes with the fume hood. And there is a room pressure monitor, which is new or.
Oh, right. We didn't talk about the room pressure monitors. We can talk about those a little bit.
Yeah, so room pressure monitoring in laboratories would be, again, something that's up to preference of the facility and the owner. It's not required in laboratory spaces. Your pressure monitors will be required more so in your healthcare and pharmaceutical applications. But we do see sometimes the pressure monitors in laboratories. Yeah, but we have a new line of pressure monitors that we just released called Loom. There's 3 different levels. We have our basic pressure monitoring, which would be our Loom 10. That's single room pressure monitoring. And it doesn't have any backnet connectivity. So if you're in a smaller facility that doesn't have a BAS system, that would be a good opportunity to kind of apply that option. The second one would be our Loom 11, and that would be our single room monitoring that also has backnet. And then our Loom 20, which is our most advanced pressure monitor, which has up to 3 room monitoring, as well as it has the ability to pull in points over backnet such as temperature, humidity, and ACH, or really any analog backnet point to display on the screen as well.
Those have to be recalibrated periodically.
So the sensor that we have for our Loom line is, we call it the SDPT, it's a flow through sensor.
Yeah.
Very, very minimal drift over time, shouldn't need to be recalibrated. However, we do accept an analog signal, so you can also use it in conjunction with like a third party dead-ended sensor. In that case, the dead-ended sensors typically will have more sensor drift over time and may need to be recalibrated. But we can do everything through, it's a touch screen room pressure monitor, and every setting can be changed through the touch screen itself. So if someone needed to rebalance their sensors, they could just go into those menus and change the scale factor, the offset through the screen without any issues. And we don't require any training for people to install and start up our pressure monitors.
Right. Well, I guess if that's it, thank you to everybody online. If you do come up with any other questions or you just want more information about these products or you need help with an application, you can reach out to me. I'll have Michael send my information out after the class. And yeah, again, thanks for attending and hope you guys got a lot out of it. Thank you, Rachel.